So I start with talking a bit about MPI, which stands for the Message Passing Interface, which is the sort of standard library. It's an API really. So it's a library specification that determines functions that need to sort of satisfy some standard in order to achieve programming distributed memory systems. There are various implementations of this library. Some, maybe most of you are familiar, for example, with OpenMPI, which is just one implementation, which is open source, but there are also vendor-specific implementations of the library, such as Intel MPI. And this is what we will also use, MPI, as the main tool by which we will do the examples for parallel programming. So in this distributed memory programming paradigm, we achieve parallelism by assuming that each process has its own memory domain, okay? So the memory that can be seen by each process is a distinct address space, let's say, compared to all the other processes. This is different from parallel programming, programming in parallel in a so-called shared memory paradigm, right? So that's the difference between distributed and shared. So what MPI functions facilitate in this approach is, okay, first of all, some simple things like obtaining environment information about the ID of the running process, the total number of processes that are running, etc. So that's one thing the MPI functionality allows you to. But more importantly, MPI is used to achieve communication between processes, which effectively means copying data between domains of the independently running processes. So this is just a picture to compare again the shared memory paradigm with the distributed memory paradigm. So in a typical node, a computer, let's say, so one node of the cluster, you have some number of cores. Here it's 4, but doesn't really matter the number of cores that I have here, which share some cache and share some memory. And so you can see from this block diagram here that these 4 cores share a common memory. Okay, so we say that they share a common memory address space. For examples of such shared memory systems are, as I said, a multi-core CPU node. A GPU is like a shared memory system because you have multiple threads that are accessing the same GPU memory, for example, etc. And the way one goes about programming these, we won't cover it here, but you might have heard of these, is like OpenMP, CUDA, also MPI, which I talked about before, can be used to program shared memory systems, but we won't get into that now. But these are the programming models that you can use when you have multiple processes that see the same memory, okay. What we will do today is look at systems like these here, where you have multiple of these nodes. I'll just call them nodes, okay? So multiple of these multi-core systems, which have distinct memory address spaces, okay? And now you want to use all these, 16 cores together. And so, like nodes in a cluster, and you need to have a way for these to communicate with each other, to share data with each other. Communicate, share data, it's the same thing. Right? So in the first case, in the shared memory model, sharing data is done via memory. So you have the same array that the cores want to process in main memory. So you just access it by multiple cores. I mean, maybe don't need to say too much here, right? So data is shared by memory. In this case, so if this core here that I'm pointing to, yes, you can. If this core here wants to access some data that is on another node, then you need to do an explicit transfer of that data from one node to the other, right? So you need to do an explicit copy over some network, presumably, right? Doesn't have to be a network, but most of the time it's a network, so that the data that was held here ends up in this memory domain, so that this core can now access that same data that was on the other node. Okay, so this is what distributed memory means. It means programming in this fashion here, where you need to explicitly transfer data from one memory to another memory in order to achieve communication, rather than, this is in contrast to this shared memory approach, where the processes see the same memory. Okay? So this is what this introductory session is today, right? Until the coffee break, to give you some basic concepts of how you go about doing this, some introduction to MPI with some first functions that one learns in order to do this kind of program. Okay. So trivially, running a program in parallel. So if you have any experience with Linux, you know that you can, so just ignore this SSH node 1, right? So I can just run a Python script, put an ampersand at the end, and then this script is run in the background, right? And so if I stack, 3 of these like this, then these 3 will run in parallel in the background. So that's a lazy way of achieving some form of parallel processing. I can also do this on multiple nodes. So say I have 3 nodes on a cluster. Their host names are node 01, node 02, node 03. Then if I do this on the terminal, then these 3 scripts will run in parallel. The first one will run on node 01. The second one will run on node 02, and the third one will run on node 03. So they will just run identically on those 3 nodes. Maybe you have something in the script that says, if I'm node 1, do something else, and if I'm node 2, do something else, so that they do something different rather than exactly the same thing. But otherwise, they will run identically, okay? So that's, as I said, a lazy way to achieve parallelism. An MPI program is sort of run in a similar way. So you basically are doing this also when you run a program using MPI. You are sending the same executable to different nodes to run. The difference is that you are wrapping it in an environment where there is some functionality that allows you to also, at some points of the program, exchange data between the 2 scripts. Okay? But otherwise, right, if there's no MPI in the program and you run it like this, then it'll run exactly as if you would run it like the first example I have highlighted there on the top. Okay? So that's a convenient way of thinking about how you run this program in parallel, right? So you're running the script on node 1, on node 2, on node 3 in parallel, but there's some MPI, magic in there at some points in order to achieve some data exchange. Okay, in practice, you don't ever need to specify the nodes that you're going to send it to, but you would run it something like this, and there's some environment that has already set these 3 nodes as where the script will run. So usually you just run it like this. Okay, we will be using, I just want to say this so that if you're on a different system, you're not surprised. Depending on the system, you might not use MPI run, you might use MPI exec. Some other implementations of MPI use MPI exec rather than MPI run. Sometimes you will see srun being used instead of MPI run. They're just different, implementations of the same thing. Okay, they take similar arguments. So what we say here, we will be using MPI run. On another system, you might be advised to use srun. Just know that everything we do here could map also to there. So, yeah. Okay. So an MPI program includes calls to MPI functions. So if you're going to use C, that means you need to link to an MPI library. We will be doing our examples in Python. So what we need to do is load an appropriate module in our program, which includes the MPI functions that we will use. So in C, you would include a header file like this. And then when you would compile your parallel C program, you would use some, you would link to the MPI library, something like this. You don't necessarily have to do it like this because usually MPI implementations include a wrapper compiler, MPI-CC, that will add these flags for you, MPI-CC. So that's if you're interested in C. I just put that there informatively. But we won't be using C. We will be using Python for our examples. So in Python, the MPI library is implemented in a module called MPI for Pi, right? So at the top of your file, you will put import MPI for Pi, or more commonly, the common pattern that people use is from MPI for Pi import MPI, which is the main sort of submodule under which all the functions that we will use under this, uppercase MPI module are all the functions that we will use here. So at the top of the file, you will see in an MPI Python program, you will more commonly see this line. Okay, in C, MPI functions begin with the MPI underscore prefix, and you would call MPI init at the beginning of the file. But in Python, the initialization happens basically here when you do this from MPI for Pi import MPI. And just informatively in C, before the end of the program, you would typically call MPI finalize. So every MPI function in a C file will come between MPI init and MPI finalize. In Python, you don't need to worry about calling this finalize function. Okay. So speaking about initialization, so for some of this introductory stuff, I also have the C version here on the left for those who are interested, but I will drop showing the C version at some point because we'll just focus on the Python version. But this is just to communicate, let's say, that a lot of the functions that you have in Python also map to C functions and vice versa. But anyway, so the two functions you will almost always call in an MPI program is this function here, MPI.comSize, or in Python would be MPI.comWorld.getSize, which returns the number of parallel processes that are currently running. Okay, so the number, so if you run your program on 7 nodes, then this should return the number 7, right? So that you know how many processes are running. Remember, you are running 7 versions of the script in parallel, and you want to know in each one of the scripts how many are in this group. That's what you're doing here. So you call this function, it gives you the number 7. Then MPI.comRank determines the rank of the process. So it gives you a unique number for each running process from 0 to the number of processes minus 1. Okay, so again, remember remember the example I gave you. You're running these 3, or I don't know, let's make it more interesting, 7 processes parallel. There, and you call this function, each one of, right, and each one of this parallelly running scripts calls this MPI-com rank function. One of those, guaranteed that one of those will return 0. For another one of those, it will return the number 1. For another one, it will return the number 2, etc., up to the number 6. So each one will get a unique ID. Okay, so this is the first example of a function that returns a different value depending on the instance that's running. Okay. So this can be used, of course, to differentiate between the parallel running processes. This is the pattern that you would use typically to call these functions. So in C, you would call MPI-com size, and the number of processes and the rank would be an argument to the function. In Python, it's the return value of these functions, right? So you call nproc equals MPI get size, and rank equals MPI get rank. Okay, so this this variable that I'm putting here, MPI-com world, and which also is trailing here this after this MPI module com world. So this is called an MPI communicator. So in MPI, a user can partition the processes into subgroups, and this is equivalent to defining so-called communicators. So a communicator is just a group of processes, okay? By default, when you start MPI, so when you call from MPI for Py import MPI, the default communicator is initialized, which includes all the processes, which is called world, right? So that's all. I just need to explain to you what this MPI-com world. So we won't be covering here any other communicators than MPI-com world, but you know, just be aware that there is this functionality in MPI if you want to use it for something more advanced. Okay, note that there can be no assumption safely made about the order in which each rank runs. Okay, so you run it the first time, then maybe you see this print statement from rank 1 be printed first, and then, I don't know, rank 0 is printed last. You run it a second time, the order might be different. Each process will read the print statement at an undetermined time, and practically you will get random order of the results, okay? So unless you explicitly synchronize your processes, you can make no assumptions about the order in which things run. Okay, so here's, you would run this program. So in C, you would need to first compile it and then run it with MPI run. In Python, you would just run it like this, MPI run minus n. Here I'm using 5 processes. And then in some random order, you would get one line from each process. Okay, so see, you have one printf statement here, just to explain this again a bit better. So you have one print statement here in the script, and you're running this 5 times in parallel. And as I said, each one will get a unique rank from 0 to 4. So note here that the order is random. So unless you do any explicit synchronization, the order of will be random. Okay, but most so-called collective operations will implicitly synchronize it. And this is my segue into the first set of MPI functions that we will learn today, which are so-called functions. Okay, so collective operations mean that all processes are involved in the communication. Okay, this is opposed to point-to-point communications, which we will see later. Excuse me. So some examples of collective operations are so-called broadcast. So a variable from one process is copied to all processes. A so-called scatter operation, where the array are distributed from one process to all processes. And then a so-called gather operation, where the elements, some small arrays that are sitting on all processes are collected into a larger array on one of the participating processes. Okay. And then there's a so-called reduction operation where, for example, what you can do is you can sum a variable over all processes, right? So if you have a value which is different on each process and you want to do a sum, then you could do two things. So you could either gather the numbers and sum them on one process, but more conveniently, you have a dedicated reduction function, which will do the sum within the function over all the processes. Okay, so here's a pictorial representation of the three first functions. So a broadcast operation, so you have an array here which has 4 elements, and you want these 4 elements to be broadcast, right? To be copied exactly as they are to arrays on the other participating processes. Here we have 3 processes, right? 0, 1, and 2. So you call the broadcast operation, and this array is just copied to everybody else. Okay, simple enough. Okay, a scatter operation is similar, but not exactly the same. So for example, here, process 0 has an array with 6 elements, and you have 3 processes in total, including process 0. Okay, that might not be obvious at the beginning, but including process 0, you have 3 processes which have allocated their own smaller arrays, each with 2 elements. And so a scatter operation, what it will do is it will take 2 first elements of the bigger array and put them in the 2 elements of process 0. The next 2 elements in this example of the bigger array and put it in the 2 elements of process 1, and etc. until the last process. So when you call it, you need to be a bit careful that the number of processes and the number of elements match, right? So that this can work. And then the gather operation is just the opposite of a scatter, right? So you can probably imagine what this does. So you have the little arrays on the processes, and you want to collect the data into a bigger array on one of the participating processes. Okay, just one thing to note is that process 0 is participating on both sides here, okay? So usually when you scatter, for example, then the process that holds the big array will also need to hold the smaller array, right? Even though it already has that data. By symmetry, this is how the MPI functions are specified, that basically process 0 has to send to itself those 2 elements. Okay, that's just a sort of peculiarity that might not be obvious, but you should keep in mind. Okay, and the same with a gather operation. Okay, I just want to run through the signatures. This is not that, just to see exactly what you need to specify in each case, right? So in a broadcast operation, and let's just look at the Python implementation of this function. Basically, all you need to specify is what you want to broadcast and who holds the original version of what you want to broadcast, which usually is the process with rank 0. Okay. So 2 arguments, the buffer and the root process, as we call it, which holds the data. So in this case, the root process is process 0, and almost always it's 0 because you write your program in a way so that it works with how many number of processes you're running it on. And process 0 is always present, right? If you run it with one process, two process, any number of processes, there will always be a process with rank 0. So that's why usually the root process is set to process 0. Okay, so an example, broadcast from the root, the 4-element double precision array R. So in C, you would need to also specify the type and the number of elements in the array. In Python, these are all inferred from the variable itself, right? Because Python has ways to know the type and the size of the array. So you would just call something like this in Python. Here's a bit of here's this bit of an edge case. Let's say you want to broadcast a scalar variable. In Python, you need to turn it into an array first, for example, using a NumPy array, and then send it over, right? Because it needs to get its size. Okay, so one way is to, it's not the only way, but a common way is to turn it into a single element array before you broadcast it. Okay, in C, the data type is important because in C, there's no way to know the type and the number of elements. You just set a pointer here. In Python, this is easier, right? So you just have, as I said, the variable and the root process. Okay. That's not so important. So, okay, so then we look at the signature of the scatter operation. And again, I'll ignore the C stuff here. Maybe we can just focus on the Python just to see what you need to specify, right? So you need to specify 3 things. Again, let's go back to the scatter operation just to remind you what it is. So you have a big array on the root process, and you're distributing it basically to little arrays in the other processes in the group. So you just specify first the send buffer, so the big array, then the receive buffer, so the smaller arrays, and where this, so this root rank, this is the rank of the process that holds basically the send buffer. So some examples here. Again, I have this in C if somebody's interested, but I won't say too much. So for example, if you have, this will only work, what I've written here, these 3 lines here, will only work if I have 3 processes. So this process 0 will have some random 12 element array here, and I want to distribute it to 3 processes. So I need to have an array on each process. I need to have an array with 4 elements, right? 4 times 3, 12. So this is the sending, this is the receiving array, and the root process is 0. Okay. Again, a bit of an edge case. Let's say I want to distribute, let's say I have a 4-element array on the root process, and I want to distribute it to 4 processes. So I want just 1 element to be sent to each process, right? So now I want a scalar to reside on each process. Then typically what you would do, again, this is not the unique way of doing it, but it's a common way of doing it. You would allocate a 0-dimensional array as the receiving buffer on the processes for the scatter. Okay, that's just this is the tricky bit in Python that you. So if you say here element equals none or something like this, which doesn't have a size, then MPI will choke on that and tell you the receive buffer you gave me does not have a size, right? So you need to specify element to be something which has a which has a size, even if it's 0. Okay, and then the gather operation is just the reverse, right? So even if I didn't have this slide, you could probably guess what the arguments would be. So again, the order is first you put what you want to send, and then you put what you want to receive. But now what you want to send, I'm going back to the pictures that I was showing. But now what you want to send is the smaller arrays, and what you want to receive is the bigger array, right? So it'll look something like this. So in this case, collect a 9-element array at process 0 by concatenating 3 elements from each of 3 processes in total. Right? So on the root process, you need to initialize an array which has 9 elements for this to work, at least 9 elements. And then if you want to do a scalar, then again, the scalar needs to have a size, right? So you need to have it be, even if it's a 1-element array, it still needs to be an array with 1 element. Okay, and the last collective operation that I want to show you is this reduction operation, which, as we said, what it does is it can sum, or not just sum, but you could have other operations like do a product or do some logical operation on variables that are held on all processes. So here in this example that I have here in this picture, excuse me, each process has a 2-element array. So each process has an array of size 2, to say it a different way. And what you want to do is you want to sum these arrays so what this reduction operation will do is it will sum the first element of each process and put it in the first element of an array in the root process, and it will sum separately the second element of this array, for example, and put it here in the second element of a 2-element array on the root process. Okay, so it sums element wise, right? That's what this operation. And again, this op is by default a sum, but it could be something else. So it could be product, right? You could do a multiplication across processes. Again, you could do a logical or, logical and, right? If you want to do something like this. And the signature again is the first argument is the send. So the first argument would be these arrays here, and the receive buffer, which would only be significant on the root process, would be where you want the sum to actually reside on this process. Okay. So here's an example of how you would sum a 3-element array and put the results on process 0. Okay. Okay. Yeah, again, this special case for when you have just a single number on each process that you want to do this reduction on, then you need to turn that single variable into a 1-element NumPy array. You need to initialize the sum on root as, you know, a 1-element array again, and then put these as arguments. Otherwise, MPI will not know how to get the size of whatever you're sending. Okay, some things. So I have some exercises with examples of how to use these coming later on. Maybe I'll speed up a bit to get there. But I just wanted to mention some functions that we won't cover, but maybe you're thinking, maybe you want to, you know, take a look if you have some specific use case. So as we've seen scatter and gather, but you could also have scatter V, so with a V at the end, and gather V, which is just scatter and gather operations, but where it doesn't need to be that the number of elements per process is the same. Okay, so you could have 3 elements on one process, 2 elements on another process, etc., and then specify how to collect these into a bigger array, you would use scatter v and gather v. So there's some additional arguments there that you can put in order to tell these functions that the dimensions of each of the arrays that you want to collect. All reduce is like reduce, which we saw in the previous slide, but the result is not just put on the root process, but is put on all processes if you need that. And some of these operations have so-called in-place variants, which means you can replace the send or the receive buffer. So you can sort of scatter and receive the data in the same array that you use as the send buffer. Okay, so we won't cover this, but just know that this is available to you. So here's an example of how you would use a reduction operation where the result goes into the same variable that you sort of sent. Okay. This is just informative. We won't need it later in the exercise. Okay. So before we go on to the exercises, I want to say another last thing. So what we've seen so far are collective operations. And I said at the beginning that these collective operations are in contrast to point-to-point operations. So collective operations, I said, are where all the processes participate in the same communication. Point-to-point communication is when you just have two processes communicating with each other, okay? So most common case is the so-called send and receive operation, which you need to have the two processes that are doing this communication. You need to specify a sender process and a receiver process. And the sender process needs to call a function which says, send this data to, some rank. The receiving process needs to have a function that says, prepare to receive data from, some rank. And these two functions need to match. Otherwise, nasty things will happen. In the best case, your program will stall. In the worst case, you get other artifacts. But in any case, this is how MPI implements this kind of point-to-point communication. Okay, so here is an example. You have 4 processes, right? Process 0 has an array with 4 elements that it wants to send to process 1. And process 2 has an array with 2 elements that it wants to, process 3 has an array with 2 elements that we wants to send to process 2 in this example. So here we have 2 point-to-point operations. The first point-to-point operation is between 0 and 1. And the second point-to-point operation communication is between 3 and 2. Okay? And you can see that they're different. So in the first case, a 4-element array is sent. In the second case, a 3-element array is sent. So in this case, you would need process 0 to call a function which would say send this 4-element array to process 1, but you would also need a matching function that will be called by process 1, which says prepare to receive data from process 0 and put it in this array. Expect 4 elements, something like this. And then the same thing should happen between process 2 and process 3. So process 3 should have a function called, which is a send, so that it says explicitly send these 2 elements to process 2. And process 2 should also have a matching receive function. And these are the signatures of the functions that you would call. So one is the first one is the send, and the second one is the receive. And you might, so if I just asked you without showing you this, what do you think the arguments of a send should be? Then I'm pretty confident that you could tell me that, well, I need to tell it the array that I need to send and where it needs to go, the rank of the process and where it needs to go. There's one additional argument here, which is a tag, which maybe would not have been obvious. And this is just an integer that you use to tag the message so that if you have multiple messages that are going to the same process, that you can sort of differentiate between. Okay, so that's the only additional argument that maybe would not be obvious here. On the receiving end, again, if I would just allow you to intuit with what the arguments would be, then you should be able to come up with, again, the array where the data will go, and probably the rank of the process that is sending me the data, right? Then, of course, you need a tag, as you have in the send. So if you want to differentiate between tags, then you can do it. You can also actually, what I should have said is that this is an optional argument, right? So you can just ignore the tag in Python, and it's just assumed to be 0. On the receive side, though, you can also have another variable, which is a status, which is just some MPI object that you can query later to see if the receive ended successfully and other things. We won't be looking at this here, and we will effectively just ignore this argument. So you need to specify a source rank for the send and a the other way around. You need to specify a source rank for the receive and a destination rank for the send. And you can use tags to differentiate the messages, or you can just ignore the tag, in which case it doesn't really matter if you're not sending multiple messages to each process. Okay, so here's a trivial example. You have some process I, that wants to send 4 elements to process J. Then you would do something like this. So remember, this script is being run. So this is a part of the script in a larger Python script, presumably, that you are running using MPI run. So there might be, some number larger than 2 of processes running in parallel. But all you want to do, for some weird reason, is to send from process I to process J this 4-element array, let's say, just for the sake of this example. Then what you would do is you would query the rank of the running process. And if the process would have a rank of I, then you would call an MPI send. And if the process would have a rank J, then you would call an MPI receive. Simple enough, right? So all the other processes would fall through this if statements. And only these 2 processes would be involved in this point-to-point communication, right? So some some things that maybe it's useful to say here. So if you forgot this, if rank equals J, for example, then what happens? So only rank I comes into this if statement, and the rank I sends to process J this array. But then, as I said, if you were to forget this if statement here, then all processes would call this receive function, right? So what will happen? Well, the process with rank J will exit this function because it will receive the data, but all other processes do not have a matching send, so your program will block there. Okay, this is what would happen if you would forget this if rank equals J. Okay. Similarly, if you would forget this if rank equals I, then all the other processes which are not, sorry, if you would forget this, if rank equals I, then all processes would send to rank J, but you would only have one receive. So I don't know if it would necessarily block, but probably weird things would happen depending on who actually gets to call this MPI send first and who gets to call it last. Okay. Now, the last thing I want to say about these point-to-point communications is that very often you have a pattern like the one I'm showing here, where you have a variable or an array on all processes that you want to move sort of forward or backwards or do some communication like this. So in the specific example that I have here on the image, every process, all processes want to send a variable to the next process, okay? This is what we want to do here. Now, this pattern here, the way I've put it, this will not work because the send will never complete on any process, right? Because for the send to complete, you need to have a matching receive. Everybody is calling a send, but everybody's stuck in the send, right? All processes will get stuck in the send before a receive will be posted to actually receive the data. One way around this, so this will result in a so-called deadlock. A receive can only be posted once a send completes, but a send can only be completed if a matching receive is posted. So you see what the what the problem is here. One can serialize this communication, so you can loop over the number of processes and do these operations one by one, but you don't want to do that. You want to run this somehow in parallel, right? That would in principle work, but it's a bit clunky. It's also inelegant. So what you have is an MPI function which basically implements this. So it's called a send receive operation. So it does so in the same function you specify the arguments of the send and the arguments of the receive, and it's guaranteed that it won't block as long as the send is matched with the receive. Okay. So in this case, you would do something like svar, the sending variable, send it to rank +1, and receive from rank -1 the receive variable. Okay, so you can see that the arguments that I put here are the same as I had here, right? Excluding the tag, which I just put 0 here. But this will go through. This function here will go through. The previous pattern would block if I were to write it in an MPI program. Okay, so these functions we will use in some examples just to see how they work in practice. But I wanted to give you here some additional functions that we won't see, but maybe it's useful that you know about. So some MPI functions allow you to omit the mandatory, let's say, receive buffer arguments. And so the actual receive buffer is returned as a return value of the function. Okay, so you can do something like this. So whereas in the uppercase receive, you would have this r underscore ARR variable be an argument. Now it's returned. It's just yeah. There are non-blocking variants of send and receive, which are I send and I receive. The I stands for immediate, which just means that the function returns immediately and does not wait for a matching send and receive. So this would be another way to overcome this problem that I said here. You have a where it blocks. You could use I send and I receive here. So when you use these, let me get back to, yeah. So when you use these functions, they receive immediately, but then you don't know if the message has actually been received. So what you would do is you would call it in this pattern, right? Where you return this request variable from MPI.com world. I send, and then you poll this request variable. So here's where the program blocks until the message is received. Okay. So in here, you could call in principle an MPI receive, and this will not cause a deadlock. And I think now, yeah. Okay. So, right. So what I have now is some exercises to show you how this all works sort of in practice. There's 4 exercises, and they are under this directory on the cluster. So if you registered early enough to get accounts, or if you have accounts on the cluster, then please follow my lead here. I'm going to bring in a terminal, and I'm going to log into the cluster. And yeah. Okay. Just give me a second. Okay. Is that large enough? Yes. Hope it's large enough. Okay, so I'm not on the cluster now. This is how. Okay, yeah, okay. I have a few more lines here than necessary. Don't worry about that. So this is how you would log into the cluster. If you should have gotten in, as I said, if you registered early enough, you should have gotten instructions how to do this. So there we are. Okay. And there are 4 exercises. Which I will copy to my home well, maybe I make dear, I don't know, EuroCC training exercises. You don't need to create this directory. This is just so that I don't interfere with other stuff. Okay, and now I can copy these. All right, so let's see. Yes, so you see there's exercise 1, exercise 2, exercise 3, exercise 4, once I copied this directory. Okay. Now, if you don't belong to this group, you might not have read access. Yes, is that the case? Yeah, I can probably fix that. Or can I? Let me see if I can fix that. LSD. Yeah, okay, this should be possible. Let me see. Yeah. Now you should, even if you're not part of this group, as I said, this group is for those that were created accounts under this training event. But now everybody should be able to copy. Give me a thumbs up, thumbs down, something. Good. Okay, let's go. So, so I assume you already know how to log in and that you have had some training for example, the previous training in the series, where you use Slurm, the job scheduler, sbatch, sq, these commands. Just a bit about the structure. Each folder includes an exercise Python file and a submit script. And the workflow will be, you need to modify the Python script, you submit the job, sbatch, sub, x, and then the number.sh, and then you look at the output to see if you did it correctly. No job should take longer than a minute to run. So if it takes more than a minute to run, then maybe you did something wrong. But that's unlikely. These are easy exercises. So the exercises are basically mostly complete, except for some lines that you need to basically rewind these slides, look at the functions we defined earlier in the slides, and sort of replace the arguments of some of the functions that you need to use to complete the exercises, right? But so exercise 1 will give you a demo of using get rank and get size. Exercise 2 will give you a demo of using broadcast, scatter, and reduce. Exercise 3 uses gather, and exercise 4 uses the previous ones plus the send receive. Okay, so this is what you need to use. It's also said in the comments, but this is basically what you need to use for each of the 4 exercises. Okay, so I have run these exercises using these modules. So please use these modules when you, well, I mean, they're also in the script, so you don't necessarily need to load them, to be honest, but I don't know if you're going to do anything interactively or something like that, then I'd encourage you to first purge so that you don't have any other modules, and then load these modules. And now you have MPI for Pi and NumPy, etc., and the correct Python version loaded. Yeah. Which is this one, which these have been tested with. Maybe others will work too, but I've just tested them with them. Okay, exercise 1. Let's see. So I will cd into ex01. There are 2 files, xeo1.py and sub xeo1.sh. So this is the Slurm script which will run it. And this is the Python script that I want you to modify. You can use your favorite editor to open the script. And so this is easy. This is the easiest exercise. We start from an easy exercise. Complete the MPI functions here. So I want to get the rank, and I want to get the number of processes. And these are then printed to the screen, as you can see here. If I leave it as it is, this is an error because there's nothing after the equal sign. I need to write MPI dot world, and then get rank, right? So, well, I'll save that for later, the comment for later. Then I can just, then I need to call get size, save myself some typing by just changing this to size. All right, that's all you need to do here, just to warm up. The other file that is in this, so that's me. Okay, so I'm done here. The other file in this directory is the shell script, which is the Slurm submission scripts. Okay, so I'm only looking at this now because if you are not part of this Edu21 group because you didn't register or you registered late or I don't know, whatever reason, you're using your personal accounts, then these two lines will not, these two lines will block you basically. Because we have a reservation on some nodes that is only good for this project. So you should remove those two lines and then submit the script. And if there are free nodes, then you will run. If there are no free nodes, you will not run. But that's what you get for not registering. Okay, so what do okay, so I want to use two nodes. Total tasks is 8 and 4 tasks per node. And you can see here that basically where the actual stuff is happening is here, where it's MPI run Python ex01.py. Now, what will happen here? As I said at the beginning of the slides, it's as if I would SSH to the nodes individually and run this Python ex01.py in the background 4 times on the first node and 4 times on the second node so that I have 8 running in parallel. The only difference is that I'm doing it via the MPI wrapper now, which means that inside the scripts, when I call MPI get rank, I will get a unique number between 0 and 7. Okay. So sbatch is how you submit sub ex01.sh. So this will send it to the job scheduler. And now if it's already done. This is the output. And this is what I get. Okay. So what I see here is this is rank number of nprog equals 8 on node either 3 or 4. So I hope you're convinced that indeed this run on 2 nodes and that indeed 4 processes run on 1 node and the other 4 run on the other node, right? And also what I said at the beginning is that the order in which you see that the different processes have run is sort of mixed up, right? So there's no explicit order here in which these processes run. So, okay, this is where all the problems surface. I can't submit. How do I log in? No? Everybody's okay? Yeah. Network, like Wi-Fi? Uh, not sure. Can you, isn't there? It doesn't matter for logging into the system, I think. Okay. Pasigainen? Okay, I'll move on to the next exercise now, so I don't swallow all the coffee break, only part of it. Okay, so the second exercise. Well, maybe I should just say, so this should run because it's not really doing anything, just printing out rank and size. And what I want to say that, oh yes, that the order is random, but basically that we managed to get a unique ID for each rank. That's all I wanted to show there. Okay, in the second exercise, what we want to do is we want to sum the contents of this text file. So that this text file has a single column of floating point numbers that we want to sum, but we want to do it in parallel. So what we want to do is perform a scatter operation so that the data of the file, well, first the file will be read by rank 0. Then we want to scatter the elements of the array to all the processes that are running currently, and do each process do the sum of the sub array, right? So it has a partial sum, and then use a reduce operation so that we sum the individual little sums to a grand total and print the result to screen. So here is the steps that we want to carry out a bit more analytically. The root process should read all elements into an array, which we call array. The root process should broadcast the total number of elements of the array ntot to the processes so that each process knows what the total number of elements is. So there you need to write a broadcast operation. Each process then should initialize an empty array, sub, with the number of elements being n total over the number of processes, which is size. The root process to scatter the elements of the array to all processes. Each process will do the sum locally and then use a reduction operation to obtain the grand total over all the elements, which happen to be 55,440, to the root rank. Okay? So you only need to complete some parts. If you do it correctly, this is the sum that you should get. And let me walk this through. Okay, so these are the contents of the EXO2 subdirectory. So in addition to the Python script and the shell script, there's this text file, which includes the elements that we want to compute. I won't go through it all because it is, as you can confirm, 55,440 elements. Still, this is not a big deal to, of course, sum 55,000 elements, but okay, this is just to demonstrate doing this in parallel. Okay, let's look at the script now, the Python script, I should say. So you only need to look at these comments which say to do, but let me walk you through it a bit. So this is just some initialization stuff here. But here, rank 0 is reading the entire contents of the text file, array.txt. And then it's also getting the number of elements basically in the array. We know that this is 55,440, but in any case, we are sort of getting it also here in rank 0. And now what we want to do is we want this number, which is only available to rank 0, because only rank 0 read the full array, and therefore only rank 0 knows how big it is, right? We want this number to be broadcast to all processes. So here there is a missing MPI broadcast command that I want you to complete in order for ntot to go to all processes. Once all processes have ntot, then the processes can compute how big the subarray they need to allocate is, which will only include part of the data, right? That will be nloc. And once we have the local array allocated, then we can complete a scatter operation, which will distribute the elements of array to the processes. Okay, once each array has a part of, once each process, has a part of the array, then you can do the local sum. But this is only the sum of the subarray which corresponds to each process. So later we need to do here a reduction operation so that overall processes, the data is summed in rank 0. And then rank 0 here prints the total sum. As I said, if you do it correctly, then you should get this number, which is given here on the slide. So this shows you how to do a broadcast, how to do a scatter, and how to do a reduction operation. I'll pause for a few minutes so that those of you who want to try it before I do it get a chance. Right, so I'll start by completing this first using the broadcast. And this takes two arguments. The first is what I want to broadcast. And as I say there in the comments, you want to broadcast ntot. And the rank that holds the value that I want to broadcast, right, is the root process with rank 0. So now after this function returns, all processes should have, in this case, the number 55,440 in the variable ntot. Okay, now nothing to do here. Nlock will be computed by ntot over size, and then an array sub will be allocated, which will have nlock elements, so nothing to do here. But here is where we want to scatter now the array. So who wants to give me does somebody know? Somebody want to try and give me the arguments to scatter? Okay, Alexi. Array, sub, and yes. So the first argument is the send array, and the second argument is the receiving array. And hopefully all the sizes will match now. They should match because we've allocated some to be nlock. And we know that there are size number of ranks, and we know the total array is ntot, so everything should work. Okay, then the local sum.
Can I ask something?
Yes,
Should we always put root equals 0 or just put 0?
Yes. So in Python, a named variable, you can omit the name if it's in the correct order. This is just the Python syntactic sugar to allow to do this, but you can also do this. Is this the question?
Yes. Also on the line of np.empty, you say equals nlog. Is this why we use a named variable and not just the variable nlog?
So the question is why I didn't do this?
Yes.
This is a bit more obvious what nlock is. I don't know. I mean, it just Python allows you to put the names of the variables that you pass, or the names of the arguments, I should say. So sometimes I decide to do it, sometimes not. It's a bit random. I don't know why I put it. You don't need to. It's not mandatory, right? But it but it makes
helps. Yes, it
makes
helps
it a bit.
maintainability. Yes, readability and maintainability of the code to put like you wrote your code.
Okay. So I'll continue to do that.
Yes. Okay.
Okay. Okay. So can somebody give me now the reduction that we want to do? So remember, now we have sum lock on each process. We want to sum the individual sum locks into sum tot so that rank 0 prints them. So basically, all I want you to give me here is the order of the arguments. Anybody? Area? Sum tot and root equals 0. Okay. Yes.
Sum operation.
Excuse me?
You should also put the sum operation.
We can. So yes, the okay, now you caught me off guard. Which is it op?
The third parameter, I think it's okay, you use named parameters. Okay.
I think it's like that, but the default is sum. I have it in the slides. Yeah, MPI dots. I hope. Yeah, I think it's op equals. Where did I? Yeah. Oh, it's big op. Like this. Okay. So now, I think that's it. Yes, we don't have any other. We do not have. No, it should be little op actually. Just want to avoid any. Yeah. So we don't have any other to-dos. The submission script is just again loading the modules and running it on 8 processes. So now I should be able to submit it. And that should be it. And if I did it correctly, yes, you see the sum that I promised you should get on the slides. I lost my place on the slides. Sorry, just let me get back to exercise 2. And just confirm, yes, that this is the same number. Okay? Okay. Any questions? All right. I will use some time from the break because I started a bit later to do just the 4th exercise. So I'll skip the 3rd one. You can you can try it at home and ask me any questions if you have any. So in exercise 4, this is a bit more complicated than the other exercise we've seen. So again, you have an array with 55,440 elements that you want to read by rank 0. But what you want to do is compute this kind of discrete second derivative on the one-dimensional data which is in the array. Okay? So you want to do array of I minus 1 plus array of I plus 1 minus 2 times array of I. The catch, okay, so you want to do this. Now, this is easy to do on one process. The catch is to do this in parallel, where each rank only has a subset of the array. Okay? what we want to do is distribute. So maybe actually I don't go through all this text, but maybe I show a picture. So you have the array here that you want to compute this this derivative on. You read it in rank 0. So rank 0 now has all the elements of the array, and then you want to distribute this to the processes. So you do something like this. Now what we do is, and it'll become more obvious why we do this in the next steps, but we actually allocate the sub-arrays with 2 additional elements, the first one and the last one, and we put the useful data sort of in the middle, right? Starting from the first element rather than the 0th element. So the second element rather than the first, and going up to there. Okay. So the blue data now, the ones that are colored in blue, or is it green? I don't know, depending on how you see it. So they're not red. Ones are filled in. The red ones are undefined. So the 0 and the 4 of each rank here are undefined. So why are we doing this? Because now if you want to do this operation that I talked about in the previous slide, let me go back to the previous slide. So you want to do this operation, right? I minus 1 plus I plus 1 minus 2I. So if you want to do this now, in order to get this operation here, you want to do let's focus on rank 1. So in order to do this operation here, you need to take 2 times and subtract it from this element here, but then the previous element to this element here is sitting on a different process, right? Because it's this one, right? So let's look at the global array here. You want to take this number here minus this, minus the one before it, minus the one after it. But the one before it now is sitting on rank 0, where this one is sitting on rank 1. So how do we solve this problem? We will do send receives so that we communicate the edge elements to the different processes. So we do one send receive so that this number here goes, this number here, I should say, the one I'm pointing to now, goes up to the previous rank and fills in this extra element here that we left unallocated, right? The same happens for all the ranks. Then we do it again in the other direction now, so that this element now goes down to the next rank and fills this element here. So now, once we complete all the send receives, then this number, if I carefully point to it, is identical to this one, the 3 and the. Am I coming through here? This number here is identical to this one here, right? So you've done the communication so that you have the edges completed, and now you can do this derivative, right? So now the derivative can be done because all the dependencies are there. So the neighboring terms have been filled in. And then you gather this back in rank 0 and you write it to a file. And if you did this correctly, I set up the array.txt such that the derivative is 0, right? You can trivially fill in these numbers so that you make sure that the derivative is 0, except for the edge cases, because there's some singularity, right, at the edges. But everything else should be 0, and you should be able to confirm this by looking at the file that will be produced. So what do you need to complete in order to do the exercise? You need to do the scatter operation correctly. You need to do the 2 send receives correctly, and you need to complete the gather operation correctly. So let me cd into the direct, oops, misaligned fingers. Okay, so there's the array that you want to compute the derivative of. And this is the program that you want to modify. Let's see the to-dos, and I'm a bit short on time, so I will maybe just call upon you to give me some to help me out by completing it immediately. Just a second though. Oh. Okay. Okay, so the first one is to broadcast NTOT, which is the same as before. So actually, I will just immediately write this here. No, icon world, bcast. Okay, this is just to broadcast the number of elements so that, just like the previous case, we compute the local number of elements, but now the subarray has two additional elements, right? Which are these boundary variables that we want to fill in later with the send receive. So in the scatter, again, I'll focus on this picture. The scatter needs to be done such that the data go in the middle of the subarray, right? So they start at element 1 rather than 0. So we use Python slicing to do this. So the array that we will send is just array. That's fine. But then where we receive it will not be just plainly sub, but we need to start from the first element and go up to n log plus 1. Okay. So now this will have the right number of elements and will also leave undefined the 0 and the last element of sub, so that we can fill it later in with the send receives. Okay. Then we need to do two send receives, as we showed, right in the, well, I mean, you can interchange which send receive you do first and second. That's not very important, but you need to do two, because in the first case, you are sending to the previous rank and receiving from the next rank, whereas in the next case, you are sending to the next rank and receiving from the previous rank, as is shown here. And I think the order that I wrote these comments is the order in which it's also on the slides. So first, you need to send the appropriate element of sub to the process in the backward direction. Okay, so when you send in the backward direction, so you send like this, then the element that you want to send is sub element 1, right? So that's going to be your send buffer. Send receive. So I want to send a sub, and I'm just going to slice it like this so that it's actually an array and Python can get the shape of this object. And I've already conveniently defined which rank is the next rank, implementing some periodicity so that the last rank loops back to rank 2, so that the last rank's neighbor in the forward direction is rank 0, and the first rank, so rank 0's neighbor in the backwards direction is the last rank. This is what these modulos do here. So I want this to go to rank B. The tag is 0. And then I want to receive it in, let's look at the picture again. I want to receive this in the last element of the subarray. So that means that the received buffer will be -1. And I should receive this from my next rank. Okay? So this implements the first send receive, where everybody sends to one rank before them, and everybody receives from one rank after them, right? So now we want to do the opposite, and to save some typing, I will copy paste this. Oop, I didn't copy paste this. Let's read the comment. Send the appropriate element of sub to the process in the forward direction. So now I want to send in the forward direction. So I'm looking at this picture here, where this element is sent to the next rank. So again, I'm going to use slices here. One element slices. So this is not the last element, but the second to last element. I'm sending it forward. The tag here is 0, and I want to receive it in the 0th element, right? So I don't want to put just 0 here because this doesn't have a size. But if I do this, then this has a size. And okay, and the last thing I want to do then is gather. So this derivative here is computed. This derivative here is computed locally. And now I just want to collect it in the nTOT elements that I allocated on rank 0. So this requires a gather operation where I send now deriv lock, as is shown here in the picture, has actually more elements than I actually need because it has the same size as sub. What I really want to send is only these colored elements here in the middle. So I will slice it from 1 to -1. Put it in the global derivative and say that I want this in root 0. Okay, so I should be able to run this now. And this file deriv.txt, as I said, should be all zeros except for the edges, which have these singular values because, yeah, there the derivative is sort of infinite because you go. Okay. So I sort of sped through that last one because I'm out of time. But are there any, but you can, surely you can try this later on offline and come back to me. But are there any questions now about anything I did which was unclear? Okay. If not, thank you. And I guess we have a break for how long? minus 1 minute. 15 minutes. Okay. So we break for 15 minutes and then we continue with Simone.